Problem 11.97. An airplane used to drop water on bushfires is flying horizontally in a straight line at 315 kilometers per hour at an altitude of 80 meters. Determine the distance d at which the pilot should release the water so that it will hit the fire at B. Okay, so the idea here is that we want to actually make the water hit precisely the beginning of the bushfire, so here on B. And this plane is traveling horizontally, and it has a certain velocity to it, which is given, and whatever water it's carrying, obviously, is traveling at the same speed as a plane, right? Now, the trick here is that we're not really interested in the plane, we're just in the water. So we can forget the plane, just think about what's going on with the water. Okay, in terms of statement, important things are here. It's flying horizontally. Okay, so, and it's in a straight line. So pretty much what this is saying, it's not going up or down. So if it's not going up or down, just traveling horizontally, the velocity that's been given to us has nothing to do with the y direction, right? It's only for the x direction. And the way we're going to solve this is precisely separating the y and the x direction. Because when the water leaves, the only force acting on it will be the gravity, right? Will be gravity. And we know there will be acceleration due to gravity. So when it leaves the plane, it's going to go out from rest because it's flying in a straight line. There's no velocity on the y direction when we first start the problem. And then it's going to leave, accelerate, and eventually it's going to hit the ground. Okay, what about the x direction? Well, the x direction is going to be going horizontally, and it will fly for as long as it can, right? There's no forces trying to stop it from going horizontally. So it's going to keep going horizontally all the way until it reaches the ground, and then the friction of the ground makes it stop. So our idea here is to decompose these two forces, so these two vectors, I should say. One vector is this y vector here from when it is released to when it reaches the ground. The other one is the x1 that's going on this direction. And if we combine the two vectors, we're going to end up in the beginning of the bushfire. That's the idea. Okay, so let's forget the plane for a bit and just think about the water. So just doing the water as my control volume. Well, the water is traveling horizontally at 315 kilometers per hour, which is the same thing as 87.5 meters per second. Don't forget, you can always convert just by doing 1 hour is the same thing as 3,600 seconds, and then multiply everything by 1, so you're always keeping the same magnitude, right? Just changing the units. And then on the x direction, there's no acceleration whatsoever. But on the y direction, we do have gravity, so therefore we're going to have the acceleration due to gravity. Velocity-wise, there's no velocity on the y direction, right? So VO naught is 0 because it's traveling on a straight line, right? And this would be our Vx naught, or VO not x. All right, cool. So how are we going to solve this? Well, I'm going to first try to find out how long it takes for the water to reach the ground. And once I have that, I can apply that time to this horizontal distance that's traveling. And I can find out how long it's going to take for the water to hit the ground and how long it will have traveled on the horizontal direction. All right, so let's just do basics. Acceleration is how the velocity changes with time. Okay, in this first case, I'm just interested on the y direction, so I'm just going to do y acceleration, y velocity. And we also know that velocity, in this case, velocity y, is how my y position is changing with time. Right, we can combine these two, and you can show that the acceleration can also be understood as the velocity multiplied by how the velocity is changing with position. All right, so note that over here we have an equation that relates acceleration and position, and over here we have a relation that relates acceleration and time. I'm going to combine those two. Okay, so I'm going to use those two equations to solve this. Let's start with this one. Okay, the ay dy equals Vy dv. From where to where? Well, from the y, I want from where the plane is to all the way until it hits the ground. Okay, so that's going to be the full height, the 80 meters in this case. And over here, so I can actually do from 0 to 80 if I want to. Let's do that from 0 to 80. And over here, the v, I'm going to from v naught to final v, which I don't know, by the way. Okay, acceleration is constant. It's because we only have gravity. The gravity is not changing with the height. Well, it is, but not for this case. We're not considering that. So ay times 80, or times height, let's just see, 80 times 80 has to be equal to vy squared minus v naught, and everything divided by 2. We know this is 0 already, so we can get rid of this. Okay, so in other words, this is saying that Vy, that is the final velocity when this guy finally hits the ground, will be the square root of AI, which is gravity, right? So this is gravity. Acceleration due to gravity. 80 being the height, and 2. So square root of all that. Cool. So this is one of the equations I'll be using. 1. Now let's go back to the time factor. So let's bring this guy down and let's solve that one. Cool. And this one is saying that the acceleration in the y direction is just how the velocity in the y direction is changing with time. So therefore, probably then this on the bottom line. So let's go down here. Therefore, ay dt equals dy. So I can integrate now from 0 to t being the time at which it hits the ground, and I don't know what that is, and from v or y all the way to vy, which is the velocity when it hits the ground. And this is, again, gravity is a constant, so it comes on the derivative, so ay times t equals vy minus v naught. This we know to be 0, and this guy we know to be gravity, so this is just gravity times time is equal to the final velocity. Okay, we don't know time, right? But we do have an equation for, so let's call this 2. We do have an equation for Vy. There it is. So we can combine these two equations, and this means that gravity times time equals the square root of 2 times 80 times, what was it? Last term? Gravity. Okay, so that means, therefore, time is just 280 gravity, square root, everything divided by gravity. And this is just 2 times 80, 160 times gravity, and this 9.8 will do. 9.8 will do for precision, and we take this square root, we're going to have positive and negative, right? Both for time, so we can pretty much disregard the negative one, only goes to the positive one, and get about 4.04 seconds. Okay, so it takes about 4.04 seconds for the water to hit the ground. In other words, what we just solved is it takes 4.04 seconds for water that is at rest in the y direction and only accelerated due to gravity to get to the ground at an 80-meter height. Okay, and now that we know that, the question becomes, if it takes 4.04 seconds for the water to hit the ground, that's how long it will have to travel horizontally. And horizontally we know that my velocity x is just how the x is changing with dt. And so vx dt equals dx. And over here I can integrate. Once again, I want to go from when it leaves, so 0, all the way to 4.04, which is when it hits the ground. And over here, I want to go from x0 to x. Okay, so that means that, remember that velocity on the x direction is a constant. There's no acceleration on the horizontal direction, so it comes out of the derivative. So all this is ex times 4.04 will be equal to the delta x, the difference in positioning. Vx we have known from the start, that's the 87.5 times 4.04. This is meters per second multiplied by second, so I'm just getting the answer in meters, and I'm getting 353 meters, approximately equal to the x. Okay, so that's our answer, but let's think about that for a second. 353 meters, what does that mean? It means that if I want to do this with precision, and that's the whole idea, right? It means that if I am at 353 meters away, horizontally, away from the beginning of the bushfire, and I let go of the water, then the water is going to start falling, and it's going to fall, and it's going to take about 4.04 seconds for it to travel from where the plane is, the height of 80, all the way down to the ground. But as it's traveling, right, it's also moving forward, and that's what this drawing is showing us. So as it's traveling downwards, it's also moving forward, and it's actually going to move forward 353 meters. So as long as I am exactly 353 meters horizontally before the bushfire and I release the water, then I'm going to start putting out the fire at the beginning of the bushfire. If I do it later, that is, if I do it at any value smaller than this, so 200 meters, 150 meters, then I'm going to start halfway. If I do it before, so let's say start at 500 meters, then my water is going to start falling before I actually have the fire. Water, 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 and then I hit the fire. So I'll be wasting some water. Okay, so that's what the idea of actually calculating this, so you can know exactly when you should release the water and maximize your effort of putting out the fire.